Let's work problem number 41 on page 147. And here it is. Right here. Tilt the camera up so you can read it. It says a 2 kilogram mass, that's this mass right here, and a 3 kilogram mass are attached to a lightweight cord and passes over a frictionless pulley as shown. Right here. Okay, and then it says the hanging masses are free to move. Choose a coordinate system for the two masses with positive direction for MA up and down for MB. Create a pictorial model. Create a physical model with motion and free body diagrams, and find the acceleration of the smaller mass. Now I'm going to modify this a little bit. I'm just going to use the procedure to find the acceleration of the smaller mass here. Okay, so let's use given, find, and solve. So given, well, here this is anchored to some, here's a pulley, and here's MA. And MA is equal to 2 kilograms. Now, I'm not drawing these strings as long as they really should be. That's okay. And here's MB, and it has a mass of 3 kilograms. And what we're saying when it says it's a very light string, the mass of the string is not going to affect this problem. Okay, we're just going to say don't worry about the string. And given. And what we want to find is the acceleration of A. But actually the acceleration of A is going to be up, isn't it? Right? If you release this one's heavier than this one. So this is going to go up and this is going to accelerate down with the same acceleration, just different direction. The string is not going to stretch. Okay? So it's going to stay the same length, so they have to move together. So we want to find this acceleration. Now, here's what I'm going to do, and this is why this is going to take longer than when the bell rings. I'm going to do it the long way. But then I'm going to show you a trick, a shortcut for solving for the acceleration really fast. You can do it in one line. But I want you to see the long way to do it first, and then I'll show you the shortcut way. So let's solve it. Now, this is kind of our pictorial model of it that they were asking for. What I'm going to do now is draw a free body diagram of this guy and a free body diagram of this guy. So let's draw a free body diagram of the 2 kilogram mass. So here's mg. Now I can 2 times, the mg here is 2 times 9.8, which is 19.6 newtons. Okay, I'm just going to say that's the weight. Now here's the tension force of the string, right? The string is pulling up on this guy, but we don't know what that tension force is. But we do know this. This tension force will be greater than the 19.6 newtons. Why? Because this 2 kilogram mass is going to accelerate up. So here's step 3 of the procedure. I'm going to make up the positive y direction for this guy. And it says to do that in the book. It says, choose a coordinate system for the two masses with the positive direction up for MA and down for MB. So this is our coordinate system. That's y. We're going to make that straight up. And now let's do the same thing for B. Okay, it's a little bit bigger. And its weight is going to be, well, what's 3 times 9.8? I think it's 29.4. Is that right? 29.4 newtons. That's the weight of a 3 kilogram mass. And then we've got a tension force pulling up on it as well. Now here's the deal. Everybody listen before you get ready to leave. This string, the tension is the same everywhere in the string. When you have a string, the tension is the same throughout the string. So this tension force equals this tension force. And I'm going to make this, my coordinate system is going to be down. My positive y direction will be down. It told me to do that in the problem. Okay. Now if I sum the forces in the y direction, equals ma in the y direction. Okay, so I'm now going to do step 4 for both of these guys. Well, this is going to be the tension force minus 19.6 newtons equals m. What is m? It's 2 kilograms times a. Now here's the problem. What am I solving for? What am I trying to find in this problem? I'm trying to find the acceleration. Well, I could try solving for it here, but there's a problem. There's 2 unknowns. There's the tension force and the acceleration. I've got one equation, but 2 unknowns. I can't solve it. What I need is, if I've got 2 unknowns, I need 2 equations. 2 equations and 2 unknowns. So let's get another equation. Let's do the same thing for this guy. So this is going to be, now I've made this positive direction, so this is going to be 29.4 newtons in the positive direction, and now the tension force is in the negative direction based on how I drew my coordinate system. And this is going to be accelerating down, so the acceleration is positive. Down is positive for this guy. And the mass is just 3 kilograms times a. Now here's the beautiful thing. This acceleration and this acceleration are the same. This tension force and this tension force are the same. So I can just solve them simultaneously. And it's just an algebraic mess to do this. So let's solve for the tension force here and then substitute it in there. So this is going to take a little bit of algebra. So the tension force is going to be equal to, we'll add this or subtract this the other side and then multiply by -1. This is going to be 29.4 newtons minus 3 kilograms times a. Now I did this in one step. Just go through the algebra carefully on your own if you need to. I just solved this for the tension force. Now I'm going to take this and put it in here. So this is going to be 29.4 newtons minus 3 kilograms times a minus 19.6 newtons equals 2 kilograms times a. Now this is my unknown. This is what I want. Well, I got it on both sides. So what I'm going to do now is I'm going to add this term to both sides, and I'm going to combine these. Well, what is 29.4 minus 19.6 newtons? That's going to be 9.8 newtons on this side, and I'm going to add this over here. This is going to be 5 kilograms times a. So now I can solve for the acceleration. It's 9.8 newtons divided by 5 kilograms. And what do you get? See, that's 1.96, I believe, meters per second squared. And that is the rate at which this guy will accelerate up. Now, or 2.0. I think the book rounded it to 2 significant figures, so they called it 2.0. All right, now the bell's going to ring in about 10 seconds, so you're free to go. But I'm going to show those of you who stay, and it'll be online here, there is a shortcut where I can eliminate all this algebra and just get right to the answer. Okay, so I'm going to show the shortcut now. And I promise, for those of you that choose to stay, it'll be like 3 minutes. There is a trick.
Can never win.
Can you guys be quiet as you leave?
Sorry.
Okay, what I can do, here, let me zoom out. See, the reason I ended up with 2 equations to solve is because I drew 2 free body diagrams. But I can do this with 1 equation if I do this with one free body diagram. And what I need to do is I need to take this, and in my imagination, I need to straighten out the free body diagram. In my imagination, I'm going to swing this guy up like this, and this guy up like this, and I'm going to get this. Here's the string. So this is 2 kilograms, and this is 3 kilograms. I made this a little too big, but that's okay. Okay, so I took this guy and I just, whoop, in my imagination, straightened him out. And I'm going to make this whole thing my free body diagram. I'm going to ignore the pulley here. All a fixed pulley does is change the direction of a force anyway. So here, look, I had an mg down like this, right? This was my 19.6 Newton force, but it was going down, but now I straightened it up. So this is going to be 19.6 newtons. And this right here, it's going to be, here's the weight is 29.4 newtons. Okay, now, and these are the only forces acting. So what I'm going to do is I'm going to say, this is step 2, which is to draw the free body diagram and show the forces acting. I need a coordinate system. I'm going to make this the positive x direction. And now I'm going to do step 4. So the forces in the x equals ma in the x. Now what are the forces in the x direction? Well, I've got 29.4 newtons here minus 19.6 newtons here equals ma. But what's the total mass of my free body?
GSA meeting going on right now in room 853.
It's 5. Because look, yeah, this mass is the mass of everything that's being accelerated. Well, I've got 5 kilograms being accelerated here. So this is 5 kilograms times A. And so now I get A equals, well, this is going to be 9.8 newtons divided by 5 kilograms of mass, and I get the 1.96 meters per second squared that I got doing it the long way. But I think you can see that this is a lot less work than all of this. Whoops. You see that? But you have to have that sophistication. You have to be able, in your imagination, straighten out that free body diagram and see now how the forces are acting on your system. And that is all.